Hello everyone and welcome to our lesson on projectile motion. This is the extension 1 version, very similar to physics but slightly different in that we have to derive the formulas and the questions are quite a lot more complex. So if you haven't done physics, this will be a great video, but if you have, this is also a good video to learn about the differences between the way that we approach the questions and the different formulas as well. We'll be starting off by looking at what projectile motion is, the basics, and then going from there. We'll also take a look at the conditions and kind of assumptions that we apply to projectile motion in the Extension 1 course. But let's quickly take a look at this slide. So projectile motion is an example of two-dimensional motion. So far, we've been looking at one-dimensional motion. So in advanced, when we've been looking at kinematics, we've been looking at one-dimensional motion, where a particle moves left and right along the x-axis or the y-axis. Now we'll be looking at dimension in two planes. So this is the x and y-axis. And viewed from the side, this is what projectile motion looks like. Now, the assumptions that come with projectile motion, and we'll get into this a little bit more later, by the way, but the assumptions that we'll be looking at for the Extension 1 course is that a projectile is a point. So the reason why we specify this assumption, the phys kids might have a better understanding of this, is because if you make an object large, so let's say that we're projecting maybe like a soccer ball, for example, that ball will encounter air resistance and will encounter other forces that may take away from this perfect idea of projectile motion in two dimensions. And that brings me on to the next assumption, which is that there is no air resistance in these questions. Now, in real life, there will be air resistance, so we won't have a perfect parabolic path like we have in the questions that we'll be doing, and that just helps to simplify the calculations. The other thing is that the only force that's acting on the projectile is gravity. So that's a constant downward force, and we'll get into that more later when we go to derive the equations of motion. But this is the same assumption as we have in physics. And the last thing is that the acceleration due to gravity is 9.8 meters per second unless otherwise specified. So sometimes they'll specify it to be 10 meters per second squared, or sometimes we'll be doing just pure calculations and having the having the acceleration as g in its kind of algebraic form when we go to derive different formulas. So those are the assumptions that come with projectile motion. Okay, now let's kind of get more into the mechanics of what projectile motion is. And the phys kids will have a bit of a leg up here, but that's not a big deal because we'll cover it off here anyway. So the key idea behind projectile motion, the reason why we can do questions with projectile motion, is that we can split this motion, this parabolic motion, into two independent motions, a vertical and a horizontal. Now, if you haven't done physics, or maybe if you have done physics but you're not too clear on projectile motion, the best way to think about this is imagine that you're standing on one side of the classroom. So imagine someone standing on the classroom on this side here, and they're throwing something across the room, and you're viewing it from the side. Now, when they throw it, what you would observe is that the particle goes in this parabolic path. And if you kind of like took a video of it and you trace it out, the path that you would see is this parabolic path. Now, if instead you're looking at it from the side, if you looked at it from the front, so say that you were like standing here and you're looking at your friend directly who was throwing the ball or whatever they were throwing, what you would see, and this is also if they threw it perfectly in line and it didn't like go to one side or the other, they threw it perfectly to you, and that's the assumption with projectile motion as well. Then from the front, what you would observe is a ball literally just goes up and then it comes back down. The same as throwing a ball just up in the air and then catching again. Like literally that's the vertical motion with projectile motion, with throwing an object in this parabolic path. Now, the top view, so this describes the horizontal motion. So imagine that again, someone is throwing it across the room, but instead you're like looking at this person, at this motion from the roof. what you would observe is that the projectile literally goes across the room at a constant speed. So these are the two independent motions that make up projectile motion. One is a vertical, that's the same as throwing a ball or an object up and down. And just imagine that the projectile, as you throw it up, it slows down, comes to a stop, and then falls back down. And then the horizontal motion is just a constant motion moving from one side to the other. Now, the horizontal motion, because it's constant in speed, it experiences no other forces. Remember, before we said that the only force that's acting on a projectile is a force due to gravity. So that means for the vertical, which is impacted by the force of gravity, that's the only force that acts on the vertical. And just to recap that, the horizontal experiences no forces, so the horizontal motion experiences no forces, which is why it's a constant motion, and the vertical experiences a force due to gravity. And that's why if you throw a ball up, it goes up and it slows down until it comes to a stop because gravity is like pushing against it as it's going up into the sky. And then once it's stopped, gravity pushes it down and the ball or object accelerates downwards until it hits the ground. So that's the basis of projectile motion, and hopefully that makes sense. The best way to understand this, and this is what the advice I give to my physics students as well, is try to think about this in a real life application. In fact, like if it doesn't make sense to you in your head, just go outside with a friend and throw a ball around, and you will see that, from these different views, and the projectile motion acts in this way. So from the front, you'll notice it just goes up and down, and then a top might be hard to see unless you've got a drone. But you could also watch a YouTube video on this and to see how this works in a simulation. I might link that if I can in the description. Okay, but this is the basis of projectile motion. And what we'll be doing in this video is we'll be deriving the different components and we'll be deriving the different equations of motion. So let's start off with the horizontal components. Now, at this point in time, you should have done some basic kinematics equation derivations. So I'm assuming that you already know how to do that, how to get from acceleration to velocity, then velocity to displacement, and then the other way around. If you haven't done that yet, hopefully it still makes sense as we go through this. Okay, let's start off by deriving the horizontal components. Now, for these equations, what we'll be assuming, or not assuming, but the scenario that we'll be looking at is a flat projection. So this is the most basic type of projection where we launch it from the ground and then it comes back to the ground. As we go to do the questions, we'll see different scenarios. So for example, launching from the top of a building is a scenario, or another scenario is launching from the ground to get to a top of a building, or in more complex questions, we'll be launching through a hole, for example, in a wall. And the reason why we look at this most basic one is so that we can understand how to derive the equations and how to manipulate them. That's why it's really important that you don't just memorize the equations, because when you get faced with different scenarios, you'll need to know how to manipulate those equations so that you can, apply it to the specific scenario that you've been given. Okay, so let's start off with the most basic of projections, which is from level ground. Okay, if we're launching from level ground, let's look at the initial condition. So this is when t is equal to 0. We'll have our acceleration function, and I'll kind of use some more basic notation here. So I'm going to go a for acceleration and subscript x, just to denote that we're looking at the horizontal. The acceleration in the horizontal is 0. So remember our assumptions, there's no forces acting in the horizontal plane, in the horizontal direction. So the acceleration in the horizontal is 0. Our velocity, our initial velocity will be v cos theta. So let's actually take it one step back and understand why this is. If we look at this side view here, when I drew this, what we had was some additional information that I didn't talk through at the time. So when we go to launch something, we give it some initial velocity. Otherwise, we wouldn't be able to launch it. So we give it some initial velocity and we launch it at some angle. So let's just say it's theta in this case. And what we can do, if you think back to vectors, is we can split this into a horizontal and a vertical component just by using trig. The horizontal component will be v cos theta, and the vertical component will be v sine theta. Now, we do need to add some additional detail here. And the reason I haven't done it straight away is because it's a little bit confusing. It's a little bit like daunting because there's so many like different components to the notation. But this initial velocity is actually a vector. So we should denote it with a squiggle, and it's also a function of time. So I will have it as v of t. Now, I won't go in and adjust these just yet because I don't have enough space, but what I will do is I'll adjust it here. So if I'm looking at my horizontal component, this will actually be the magnitude of my velocity vector. So my velocity vector is denoted by what I've just circled, and the magnitude I denote by looking at the absolute value, because what we want is not the direction, but just the magnitude, and then multiplied by cos theta to get this horizontal component. So again, just some trig there, and then cos theta to finish it off. So essentially, if the v cos theta made sense to you, I'm just rewriting this v with a proper notation that we need for these projectile motion equations. So all this is saying is the magnitude of the launch velocity multiplied by cos theta to give us the horizontal component of the launch velocity. And finally, the last initial condition, my displacement, is I'm going to denote by r of x. These, by the way, are all functions of time, but I've just left out the of t component like I did here. That's just to keep this nice and simple. The initial displacement is 0 as well because originally we're starting at the origin. We don't have any horizontal displacement. So we're like literally starting at the origin here. Let's go now and derive our equations of motion. And here I will use a proper notation. So I'm going to say a of x of t, because this is a function of t, is just 0. So I'm starting off with acceleration, and then from there I'll build to velocity and displacement. It's 0 because we said before there is no acceleration in the horizontal component. Okay, now if we go to figure out the velocity equation of motion in the horizontal, what we need to do is we need to integrate our acceleration motion equation of motion. So that's integral of 0t. Integral of 0 is just 0, but we still have to have a plus c. Now, when t is equal to 0, we said initially our velocity is given to us by this equation here. So when I plug in 0 for t, and this is where this function notation is a little bit confusing, but my c value will come out to be, so my v of 0, so this is denoting my initial launch velocity. Well, I've actually made a slight mistake. So going back to here, this isn't actually v of t, it's actually v of 0, because this is referring specifically to my initial velocity, which would be at time 0. So I have the magnitude of my initial velocity multiplied by cos theta. So that's my c value. And then I can put this all together and say that my horizontal velocity is going to be my initial launch velocity multiplied by cos theta. Or in other words, the original horizontal velocity that I have is going to be the same throughout the projectile's journey. And that's because there's no forces acting on this projectile. And that aligns with what we said in the beginning. So far I've got my acceleration function in terms of time, over time, sorry, and I've got my velocity function over time as well. The last one that I need to derive is my displacement, my horizontal displacement. To derive this, I need to integrate my velocity function. So that's just this dt. Now this is a very daunting equation because there's so many components to it, but let's break it down. This is going to be just something that's constant Cos theta, although there's a theta here, this theta is a fixed value. So this is going to be a constant as well. So I'm essentially just integrating a constant with respect to t. So imagine that I'm integrating, for example, 2 dt. This is just going to end up being 2t, right? Or plus c. So in the same way, when I go to integrate this, this is just going to be the magnitude of my initial velocity times t and then cos theta. Then I have my plus c. Okay, now what I need to do is use my initial condition. So when t is equal to 0, we said that my displacement was equal to 0. So that means when I plug in t is equal to 0, this stuff will all be 0. And we saw that the initial displacement, is 0. So that means our c value is just 0. So then I can finalize my, let's just tidy that up a little bit. My horizontal displacement equation as this. And really what this is saying is that my displacement or distance is just speed times time. So a very basic formula because there's no acceleration. Okay, so those are my 3 equations of motion. Let's keep going and we'll have a look at the vertical components. This one is a little more challenging because there is acceleration involved, but again, nothing crazy. So let's start off by looking at the initial condition. So when t is equal to 0, my acceleration, again, I'm using just basic notation, like technically I should go a of 0 to denote that it's the initial acceleration. But my initial acceleration is just negative g. So negative because gravity acts in the downward direction. And I'm taking positive to be upwards. So normally what I can do, and if you remember your kinematics questions, you can take upwards to be negative and downwards to be positive. So to flip it around depending on your question to make it easier to do your calculations. But with projectile motion, it's best if you take up to be positive and down to be negative, like the usual intuitive directions. Because all the calculations are set up that way, all the formulas are set up that way, and it's just easier to make sense of as well. Okay, so that's our initial acceleration. Our initial velocity was this here. So that comes from our vertical component of the our launch velocity. And again, remember, this is a vector. So the 0 denotes the initial, so t is equal to 0. And this is a vector because it's got magnitude and direction. And we're just taking the vertical component. Remember, this was just a simplified version so that we weren't confused when we first looked at it. But the way to actually put it all together is this. So we're saying the magnitude of the initial launch velocity multiplied by sine of the launch angle. And now my initial displacement, that's just going to be 0 because, again, remember, I'm launching it from the origin, so from the ground, so the initial height is just 0. Okay, these are all of my initial conditions, sorry. And what we'll do now is we'll start off with the acceleration equation, which is just going to be negative g. And that's it, there's nothing else to it. And remember, like I said before, we start off with our acceleration and then we integrate to get our velocity and integrate to get our displacement. So let's have a look at our velocity equation. So again, I'm denoting with a subscript of y to ensure that I know that this is the vertical component, and the t indicates that these equations are in terms of time. And right now, they're not in any sort of vector notation, so we're looking just at the magnitudes. Later, what we'll do is we'll put these all into vector notation and summarize the formulas. So that will be, I think, on the next slide. Yep, next slide when we summarize those key results. Okay, so let's have a look at the velocity equation. I get that just by integrating my acceleration in terms of t. Okay, so if I perform this integral, I'll get negative gt plus c. And now I need to evaluate my plus c value. So when t is equal to 0 initially, this is my velocity. So I'm going to replace this with what my initial velocity is, okay, which is this. If I sub in t is equal to 0, this will go away, and I'll be left with c. Okay, so this is my c value. If I put it all together, I have negative gt plus my initial velocity, and that is my vertical velocity formula. Okay, so you can see it's a little bit more complex this time because I've got this gravity component, but it's like pretty similar to my horizontal components. Okay, the last thing now to do is to figure out the vertical displacement equation. So again, similar to velocity, I need to integrate my velocity equation, okay, with respect to t. So if I integrate this will be negative gt squared and then times by half. And I did forget to mention when we looked at this before that this is just a constant. So at the beginning of this video, I explained that g is just a constant, so it can either be 9.8 or 10. So g just acts as a placeholder for whatever value will be given. And if I integrate a constant with respect to t, it would literally just stick on a t. We just multiply on a t. Okay, and now to integrate this part, so this part of the integral, this is just a constant as well, very similar to the horizontal velocity. This component is a constant and this component is a constant. So when we go to integrate that, all I need to do is stick a t in. I like to just put it in the middle. You can put it at the end, it doesn't really matter. And then I have my plus c. Okay, so if we take a look at this equation, to evaluate the plus c, we again need to look at our initial conditions. So initially, our vertical displacement is 0. So if I plug in 0 for time, this will go away, and my vertical displacement is 0. So my c value would just be 0, meaning my vertical displacement equation is literally just this. Okay, so it looks pretty complicated, but if you just spend a moment to maybe go through the explanation that I just gave, it will start to make sense for all the different components if you missed something. Okay, now the last step is to put it all together. Now this looks even more confusing, but it's not. So let's break this down. This is our velocity equation in vector form for the projectile. So this incorporates both the horizontal component and a vertical component, and it's literally just them stuck together. So if we have a look at this, this is the horizontal velocity that we derived, and we've added this I vector to indicate that this is the component that's in the horizontal direction. And this is just the vertical displacement that we derived with a j stuck on, with a j unit vector stuck on to indicate that this is in the vertical direction. So put together, this is the velocity vector function at any time for our projectile that's launched from flat ground. And in a similar way, this is our displacement equation. So again, it's literally just the horizontal displacement with a I unit vector indicating that this is in the horizontal direction. And this is our vertical displacement equation that we literally just derived with a j stuck on to indicate that it's in the vertical direction. So this is just a compact way you can think about it to summarize the formulas for the equation of motion for our projectile. Okay, now that we've derived all of the equations, let's have a go at this basic question to put all of the gibberish that we've learned into practice. So hopefully it makes a lot more sense. Okay, let's take a look at this example. A particle is projected from a horizontal plane at an angle of 30 degrees with a speed of 100 meters per second. So what I like to do as I read the question, I like to draw a quick diagram. So a horizontal plane just means from flat ground with a launch angle of 30 degrees and the velocity, initial velocity of 100 meters per second. So although they haven't like told us this in a like a pure vector form, this is still a vector because of specified magnitude and direction. But hopefully you can see that, it's not as complicated as it seemed when we're doing the equation derivations. And what they've also told us is the acceleration due to gravity is 9.8. Now remember, sometimes it'll be 10, and sometimes they won't specify, so we'll have to use g, but that'll be very clear in the question. Before we start, let's actually look at the initial conditions and break it down a little bit more. So we're launching at 100 meters per second, 30 degrees, and if we break that into horizontal and vertical components, excuse my handwriting, it's very messy, it would be 100 cos 30 degrees for the horizontal, and for the vertical would be 100 sine 30 degrees. So what we'll say is that when t is equal to 0, our vertical velocity is initially 100 sine 30, which I'll just write as 50 actually, and then my horizontal velocity is 50 root 3. So let me just fix that up, because cos 30 is just root 3 on 2. So 100 times root 3 on 2 is 50 root 3. Okay, and in terms of our initial vertical displacement, it's just 0, and horizontal is 0 because we're just launching from horizontal plane and we're at the origin. Although this question isn't super clear on that, that's what it means. Okay, let's have a look at part A. So this is just literally asking us to write the initial velocity in component form. So in other words, just to write my velocity vector. So if I put my horizontal and vertical components of my initial velocity together, this is what I'll get. So I have 50 root 3 for my initial horizontal velocity. So this will be 50 root 3, and I'll stick on an I unit vector to indicate that this is in the horizontal direction. Then I have a positive 50 for my initial vertical velocity. So this will be 50j plus 50j. And so this is my initial velocity vector in component form. Okay, let's take a look at part B. I might move this to the next slide to give us some room to work on this, but it's asking us to now figure out the velocity and displacement equations of motion. And what we'll do is we'll do it from scratch. So if we look at the horizontal components, we'll start off with the acceleration, and hopefully this helps to put some numbers to the maybe abstract derivations that we did in the previous slides. So our initial horizontal acceleration is just going to be 0. And also for this, I won't use a proper notation just because it's a bit tedious and a little bit confusing, but we'll end up with the right answers either way. Our horizontal acceleration is 0. And to get to our horizontal velocity, remember we have to integrate our acceleration. Integral of 0 is just 0, so what we'll be left with is just a c. Let me shift this to the next slide so I can just keep writing down the page. Now, this is where I have to use my initial conditions to evaluate c. So initially, when t is equal to 0, my horizontal velocity is equal to 50 root 3. So my c value is just going to equal to 50 root 3. So I can summarize or conclude that my horizontal velocity is just 50 root 3. Okay, now let's figure out the horizontal displacement. So in order to do that, we just integrate our velocity, our horizontal velocity. And because this is a constant, I'll just stick on AT. Actually, I'll put it at the end. And again, excuse my shocking handwriting. And I'll have my plus C. Now, I'll cheat a little bit here and skip some steps. Because the c value will be 0. The reason we know that is because initially, so when t is equal to 0, this component will be 0, and my initial horizontal displacement is 0 as well. So that's what we said up here. So initially my horizontal displacement is 0, so my plus c value would just be 0. So I can conclude that my horizontal displacement is just 50 root 3t, and this was my horizontal velocity at any time t. Okay, now let's take a look at my vertical components. Okay, they've specified that the acceleration is negative 9.8, or they just said that it's 9.8, but we know it's negative because it's acting in the downward direction. Okay, so my vertical acceleration is negative 9.8. My vertical velocity I can get by integrating this, so negative 9.8 dt, and if I integrate a constant, this would just be negative 9.8 t plus c. Okay, now let's use our initial condition. So initially we said that when time is equal to 0, my vertical velocity is 50. So if I put that together, so my vertical velocity is 50 when t is equal to 0, so this part will just be 0. My c value, that means, will be equal to 50. So if I put this together, I have negative 9.8 t plus 50. So hopefully this is now a little bit less abstract with the numbers. You can see it's not that tough, it's just some basic integration. So that's my velocity in the vertical direction. Finally, I need to figure out my vertical displacement. So I can do that by integrating my velocity with respect to time. And if I integrate this, this will be negative 9.8 t squared divided by 2. 9.8 divided by 2 is 4.9, so 4.9 t squared. And then I'll have 50 t and then plus c. Now I'll cheat a little bit here as well and skip some steps, but initially I said that when time is equal to 0, my vertical displacement is equal to 0. So if I plug in t is equal to 0, this will be 0, this will be 0, and my displacement in the vertical is 0, so my c value will be 0 as well. What I'll do to save myself some hassle is rub out that plus c, and I can conclude that this is my vertical displacement equation. We're not quite done yet because they've asked us to actually figure out what the what the velocity vector is over time and what the displacement vector is over time as well. So we need to put these equations together. So I'm going to conclude that v of t is going to be this component, my horizontal, 50 root 3, and I'll indicate that it's my horizontal by sticking on this I unit vector. Then what I'll do is I'll add on my vertical velocity, which is negative 9.8 t plus 50 j. So literally all I've done is taken my vertical velocity and stuck a j on to indicate that it's in the vertical direction. And this is my final velocity vector. Okay, in a similar way, my displacement vector equation is just going to be my horizontal and vertical displacements stuck together. So what I'll do is I'll grab my horizontal displacement, which is just this, and then I'll stick on my I vector to indicate that it's horizontal, and then I'll grab my vertical displacement, and I will just, in a similar way, stick on my j vector. Okay, now I've got my velocity and displacement equations over time. Okay, the last part is to just figure out the velocity and position after 4 seconds. So I'll do that up here because we're kind of out of space down there, and I'll zoom out a little bit. So to figure out the velocity at 4 seconds, all I need to do is plug in 4. So let me plug in 4 into my equation here. So I have 50 root 3 I. So that won't change over time. It's constant, as you remember from the previous slides. And then what I need to do is plug in 4 into this component here and then evaluate this component that I'm circling. If I do that, if I plug in 4, that will give me 10.8 j. So that's my velocity at 4 seconds. And it feels maybe a little bit cheating because all I had to do was plug in 4, but that's literally what it is. That's the reason why I went to this trouble to work out this velocity vector. It tells me exactly what the horizontal and vertical components are. So overall what my velocity is, I can work out the direction of the velocity and the magnitude as well from this vector. So all the information I need from the velocity for the velocity is right there in that vector equation. And then finally, my displacement at 4 seconds. So in a similar way, I'm going to plug in 4 into this t here in this equation, and that will give me the velocity, so the displacement vector at 4 seconds. So if I do that, if I plug in t into this component here, this will be 200 root 3I plus, and if I plug in 4 into here, that will be 200 minus 78.4, which is 121.6 J. So this is the displacement at 4 seconds. So this is where it is along the x-axis, and this is where it is along the y-axis. So it gives me my position exactly at 4 seconds. And that's the example done and the derivation of the equations of motion. In the next video, what we'll do is we'll take a look at how we can derive the different key equations that we'll be looking at throughout projectile motion. So that's the Cartesian equation, the greatest height, the time of flight, the range, and also the maximum range formulas.